Hello, and welcome to our presentation. My name is Ben Brito, and my two team members are Justin Sarator and Nate Stowe. Today, we will be discussing log splitters and presenting our design for one. Many people use firewood for recreational bonfires and to heat their homes. Some of these people purchase pre-cut firewood, but many of them fell trees and process them into firewood. When a tree is cut down, the log is sectioned into 12 to 18-inch pieces. These pieces are often too large to be burnt, as they are unlikely to completely dry and may not fit in a stove or fireplace, so a log splitter is used to separate these logs into two or more pieces. The splitter shown here is a gas-powered hydraulic log splitter. The gas engine provides power to a hydraulic pump. The pump generates hydraulic pressure for the cylinder, and the cylinder generates the force required to drive the wedge through the length of the log. Note that some designs utilize an electric motor instead of a gas engine. Using a hydraulic system to convert rotational force to linear force with significant mechanical advantage is the most cost-effective method, but high-pressure systems can occasionally create problems. The primary design used to circumnavigate a hydraulic system is called a kinetic log splitter. It works by storing energy in its flywheels before briefly sending the power to the wedge using a rack and pinion. This configuration is less common but is slightly simpler. Although this design fulfills the requirements of the design project, we have been tasked with developing a unique solution. Before beginning the design process, the problem was defined. We decided to design a system that could achieve a splitting force of 5 tons with the capacity to split a log up to 18 inches in length. This is the smallest common size for a powered log splitter, so we felt this to be an attainable and acceptable goal. This is a simplified diagram of the log splitter system we designed. Here is a schematic of its mechanical elements. A gas engine drives a flat belt shifter. The forward pulley drives the forward sprockets. The reverse pulley drives the reverse gears. Shaft B drives a worm, and the worm drives a worm gear. The worm gear is fixed to a pinion, which drives the rack. The rack is fixed to a pusher, which applies force to the log. A combustion engine power source was selected due to the fact that many people split firewood in locations without access to electrical power. The Honda GX50 was selected as it is capable of producing enough power to drive the system without causing damage to certain components. Because the motor has no reverse, flat belt shifting without a clutch is used. Flat belt shifting involves using a wide driver pulley with 2 narrow driven pulleys. A shift fork is used to control the location of the belt, which in turn controls the transmission of power. Although the loose pulley is generally intended to represent a disengaged clutch, we chose to use it to reverse the log splitter. In the system shown here, a third set of pulleys is placed in between the forward and reverse pulleys to act as neutral. The second iteration of our design would incorporate this feature to reduce belt wear. Because there is no hydraulic system, significant mechanical advantage must be achieved another way. There is a 2-to-1 ratio in the flat belt shifter and an 8-to-1 ratio in the forward sprockets. The greatest mechanical advantage, however, is achieved between the worm and the worm gear, which have a 40-to-1 ratio. The combination of these gives an overall reduction of 640 to 1. Note that when put in reverse, the overall reduction becomes 80 to 1. Lastly, the rack and pinion convert the rotation of the worm gear to linear motion. Shafts A through D are keyed shafts made from 1045 carbon steel. Their diameter was selected based on the components that were fixed to them and are as follows. Shaft A is 1 inch, shafts B and C are 3/4 of an inch, and shaft D is 1.5 inches. For shafts C and D, only a radial load is applied, so adequately rated ball bearings were selected. Unfortunately, shaft B is not as simple, due to the fact that it is exposed to an extreme axial load when splitting the log. For this reason, 2 tapered roller bearings were selected. The roller bearing on the worm end of shaft B is rated for a significantly higher load than the roller bearing mounted to the reverse gear end. This is due to the fact that the axial load is significantly reduced when the log splitter is put in reverse. The highest radial load is placed on shaft A, as it is required to withstand the full splitting force. Luckily, the shaft turns very slowly, so 3 high-load bronze sleeve bearings were used. Nearly all components were selected from McMaster-Carr, excluding the drive belt and the engine itself. There are several changes that should be made to this design before proceeding with the prototype. The first and easiest change is the implementation of a neutral pulley between the forward and reverse pulleys. This would eliminate the need for belt slippage when shifting between forward and reverse. The next change stems from the fact that it is generally not recommended for a drive sprocket to be smaller than 17 teeth. The second reason to increase the driver sprocket size is to increase the speed of the splitter, as the current gear reduction results in a linear speed of 1.6 centimeters per second. This is significantly slower than competing log splitters, and replacing some of the gearing with a more powerful motor is recommended. The final and most significant issue is the cost. It is estimated that the cost of the mechanical elements is $2,449 US. This does not include the costs of the rest of the system, including the frame, wedge, controls, and safety measures, or the cost of manufacturing. Needless to say, this is not competitive with currently available log splitters with similar specifications. Although the result of this project may not be competitive in today's market, the goal of designing a system using the required mechanical elements has been fulfilled. Thank you for listening to our presentation.